Hello. Thanks to the success of being able to identify the sun, the moon, and the stars, I wanted to be able to also identify which planets were which. And in order to do that, I needed to find a formula to calculate the position of said planets. After a fair bit of looking, I found a promising website that seemed to calculate the position of all of the planets. It included a whole bunch of formulas, and part of all of the calculations will end up creating an XYZ coordinate system that will then be used to convert that into a right ascension declination. It gave an example on how to calculate the position for the sun, which I followed, and I was able to recreate all of the steps that they had. And likewise for the moon, I was able to use the formulas that they had provided for the moon. I was able to recreate the calculation example that they gave. And further down, they said for the orbital elements of the planets, you use different values for the ecliptic, for example, or for the inclination. And that to calculate the position of the planets, you essentially use the same set of calculations that were used for the moon. And I thought I was in the home stretch, but when I tried to implement it for a different date and I tried to compare with the values from Stellarium, it completely fell apart and it wasn't working properly. So I tried to do a fair bit of investigation. I looked at the various formulas to calculate the position of planets, looking at Kepler's laws, trying to implement something along those lines. I found some discussion forums where people were asking questions, and that led me to another place, namely the Jet Propulsion Laboratory, that has a bunch of formulas and similar tables like this. And despite all of my efforts, I couldn't get it to work properly. And then finally, almost out of desperation, I found this website here, which is a JavaScript-based website that will calculate the position of all of the various planets and provide right ascension declinations for each of the planets, along with an altitude and azimuth. Since they provided the source code as JavaScript, I decided I was going to reverse engineer their code and convert it into Java code for my own app. So now I can finally address the question I had: which planet is this? Is it Mars? Is it Jupiter? Is it Saturn? And so now I can draw the planets, and according to this, that is Jupiter. Just to ensure that it is accurate, I'm going to jump to around midnight tonight. And the reason I'm doing that is so that it makes it easier to see all of the planets. And so in this case, Jupiter is following the sun, which is following some of the other planets I can't even see, and it's going in this direction. So there's Jupiter as the sun is setting, and now Jupiter is below the horizon. So that would be the direction of each of the planets. If I was looking up and it was night, the sun would not be here, but east would be on the left-hand side, west would be on the right-hand side. So if I orient the camera the same way as I have in Stellarium, the sun is over here, Jupiter is to the left, I've got Saturn just to the right of the sun, Mercury and Pluto are next, followed by Venus and Mars. So they don't show Pluto, but Pluto would be around here somewhere. There's Jupiter, the sun, Saturn, Mercury, Venus, and Mars. And I was able to confirm that the algorithm to calculate the position of the planets is correct by sampling different days. So now I thought, well, what can I do with this? What kind of fun can I have with this? One thing that came to mind was that since these formulas compute an x, a y, and a z coordinate in three-dimensional space, I decided to modify the code to keep a copy of those coordinates. And with those coordinates, I was able to create a top-down view of the solar system. So the Earth, in this case, is the green dot. Since I've chosen I want to look at a heliocentric solar system, the sun is going to be in the middle. If we look off in this direction, we see Jupiter, then we see the sun, then we see Mercury, Venus, and Mars, just like that. And I can do some really interesting stuff as well, like I can go ahead and see how the planets move around the sun by day. And I was also interested in seeing what the orbits were, so I added a way of computing the position every 24 hours for a full Earth year. And you can see the elliptical orbit of each of the planets. I can zoom out a little bit. This number here, in this case, is the number of astronomical units. I've got it set to 3 right now. If I go 5, I should be able to see Jupiter as well. If I go 35 astronomical units, I can even get Pluto in there. And I was playing with this a little bit earlier, and when it comes to the outer planets, I need to go for quite some time. For example, how long does it take Pluto to orbit the solar system? About 3,000 months or thereabouts. While I was at it, part of the process of calculating the position of the planets is to turn the heliocentric coordinate system into an Earth-centric coordinate system by first calculating the Earth's position relative to the sun and then subtracting that value from each of the other coordinates for each of the other planets. And by doing that, it converts all of the planets' orbits into orbits relative to Earth. So what would it look like to map out the planet orbits relative to the Earth? Well, that looks interesting. That would be the outer planets. Let's zoom in a little bit. In fact, let's cut this back and let's go back into 4 AUs. And if I move ahead, you can see that some of the orbits look fairly chaotic. Not quite the same as if it was heliocentric. So I know that the formulas are correct because they are able to correctly predict where the planets should be in the sky. And when I look at the output of those equations, it becomes very evident very quickly that by placing the sun in the middle of the solar system, all of the planets follow very simple elliptical orbits. And lastly, being able to calculate the position of the Earth relative to the sun in three-dimensional space, I was able to calculate the orbital speed for any point in time. And I noticed by looking at these numbers that somewhere around this time, April 1st, the Earth's orbital speed is 66,666 point something miles per hour. So that's going to be it for now. Thank you for watching. If you like the video, I would certainly appreciate the thumbs up. Subscribe if you're not already subscribed. Click the buttons and comment below and do all of that other good stuff. And I'm going to see you again in another video soon enough. So bye for now.